I'm Dr. Narsinga, Professor of Physics and Research and Development Dean, Marri Laxman Institute of Technology and Management. So today I'm going to explain about quantum physics. So that is introduction to quantum physics. So why quantum physics is important? So we will explain according to what the theories are there. So classical mechanics and quantum mechanics. So initially classical mechanics is a very useful one because we required all our macroscopic bodies like rocket as well as billiard balls, whatever the things we are using, those will be explained according to classical mechanics excellently. But if the sample is very small, that means the item is very small in terms of electron or photon, like small particles, so we cannot explain according to classical mechanics. So then there is another theory came into picture, that is quantum mechanics. That is quantum mechanics is used to explain microscopic particles, microscopic phenomena such as photon atom scattering and flow of electrons in a semiconductor. So these are the properties we can explain according to quantum mechanics. So then why quantum mechanics required, why classical mechanics is failed to explain some of the properties, that is some of the properties means stability of the atom and special series of hydrogen atom, similarly black body radiation, photoelectric effect, Compton effect and specific heat of metals. These properties we cannot explain according to classical mechanics. Then there is a quantum mechanics came into picture to explain all these properties to in a better way. So that is started around 1900, that is Max Planck. So he presented one paper in a German Physical Society meeting. So that the paper is on the theory of energy distribution law of the normal spectrum. So this paper is a revolution for physics. That means all whatever we are using in latest gadgets, so that all are depends on this quantum physics. Okay, without quantum physics we cannot use these sophisticated gadgets. Okay, so then he got a Nobel Prize around 1918. That is Max Planck. He got a Nobel Prize after getting this paper. So he got a Nobel Prize 1918. Okay, so then what is the difference between classical mechanics and quantum mechanics? Usually classical mechanics, it will be smooth way, like if it is a ladder is there, you can just smoothly we can speed up with a different type of acceleration velocity, we can speed that according to classical mechanics. But quantum mechanics is different, it's like a step type. So we can make it as a 0 or 0.1, 0.2 like that. Earlier one, it will be only 0 and 1. So our earlier computer systems, it will be on and off, it will be 0 and 1 only. But nowadays 0 and 1, there is a number of points will be there. So due to that one, we are getting a lot of memory as well as the speed of the computers, everything will be depends on the quantum mechanics. That is energy levels will be different, that is a step like energy levels. So then it is first one we are doing that quantum physics is the study of the matter and energy, okay, at the molecular atomic levels. Okay, so quantum comes from the this language of Latin, that is his meaning is how much it will be. Okay, that is in terms of quantum means how much. So the quantization of energy and matter that are predicted in quantum physics. Usually the energy of any material, it will be discrete. So earlier one, it will be continuous. That means according to classical mechanics, it will be continuous energy. Whereas in according to quantum mechanics, it will be discrete. Okay, or that will be quantized. Means one point to another point, there is a quantized one. So that will be predicted in quantum physics. Okay, so now we will explain one or two points, that is where classical mechanics failed to explain this black body. So usually black body means it's since known centuries of that. So if you heating the material, any material, so it will be the electromagnetic radiation will be delivered. That means it will be the radiation will be occur. Okay, it depends on the color. If usually we in our kitchens we switch on the burner, initially it will be red color. So while going on, that means you increase the gas flow, so then the color will change from like dark red to bright red, then orange, yellow, and white, like that. So it will be depends on the temperature of that burner. So if it is usually around 550 degrees centigrade, so most of the materials it will be dark red color. Whereas it's bright red, if you want, you have to go that material, it should be 700 degrees centigrade. Then orange, yellow, it will be finally really hot one, that is white. So if you see the sun at midday, that is around 12 to 1, so it looks to be very white. Whereas in morning, early morning, it will be color will be different. So like that. So this black body, that means it's radiation, relieving radiation will be different in different type of temperatures. Okay. So how we can identify what is mean by black body radiation? So it is nothing but it will absorb the all entire electromagnetic radiation incident on it. That means, so the wherever the body, if you are keeping, so the radiation is incident on that material, all will be means it will absorb that body. So it is called it as a black body. So when same material you are heating that material, then all the radiation whatever it is absorbed, that will be, it will be means incident radiations on heating starts emitting. So that means once it will be absorbed, if you heat it will be emitted, but while absorbing it won't give the reflection and transmission. So that's the important point. If it is reflected one and transmitted one, means it won't be absorbed properly, but black body it will absorb total electromagnetic radiations. When it will be heat up, then the all electromagnetic radiations will be eliminated. So it is independent of the black body, means it's not depends on the material, it depends on only the temperature of the black body. So these radiations we can call it as a black body radiations. Okay. So this how we can experimentally we can prove this one. So we will see the second next slide. So this is the Ferri black body, we call it as a. So when the radiation, that is a ray, is entering in this black body, okay, through the small hole, it will occur a different type of like reflections. Once it will go like this, like this, like this, different reflections. Finally, whenever the reflection occurs, then it will be the some of the energy will be absorbed by this body. So finally it will be absorbed totally. So there will be no reflected back the radiation. So that means it will be absorbed, all the radiations, whatever incident on that material, it will be absorbed. So this material we call it as a black body. Okay. So this Ferri black body we will call. Okay. So then what is the different structural representation? That means how it will depends, the spectral representation, how it will be depends the black body. So means what I am saying is, if you are switch on the burner, so initially it will be red color, but it is not only red color, there is a different color will be spreading. So red to blue. So there is a different colors will be spreading, depends on the temperature. If the temperature is around 3000 Kelvin, so it will get around red color. So whereas it is 4000, then it will go to yellow color. So that means only yellow color only there? No. So it will be all colors will be appear on that burner. Burner means that material. So that means all the radiations from 0 to 0, not 0 exactly. So some 200 to, so more than means lower ultraviolet as well as infrared. All radiations will be absorbed by that radiation. If you heat up, it will be released. But maximum one will be one particular wavelength. So if it is 300, it will be red. If it is 4000, it will be yellow. If it is this one is 6000, it will be blue color. Then finally it becomes the yellow color, like that. Okay, this is actually blue color. Okay, 7000 is a blue. So these are the VIBGR colors. It depends on the temperature, the wavelength. If the temperature is lower, the wavelength, that means the color will be red color. If it is temperature is very high, the color will be like a violet color type. Okay, so red to violet, that is a VIBGR. So this wavelength, maxima wavelength will be decreased while increasing the temperature, whereas the energy is increased continuously if it is increasing the temperature. But this is the experimental observations. But earlier there is a means according to classical mechanics, it's a continuous one. Like if it is this one, like wavelength, okay, lambda, and this is the energy. So the curve will be continuous curve. It is if it is increasing the temperature, the wavelength will be decreased continuously, but energy is continuous increase. Whereas in according to experimental, it is not like that. One maximum, and in other two words, it will be gradually decreasing. That means the wavelength is gradually decreasing. One is maximum. So this means observation. This is a continuous, and this is the lower uh, energy. So this we call it as a ultrasonic catastrophe. Ultraviolet catastrophe. So that is the difference between the classical and quantum mechanics. Okay, so that is catastrophe one. So usually the black bodies we use in astronomical measurements, that is like one star to another star, what is the distance between those stars, and how far it will be. That it depends on the they will calculate according to these wavelengths, the how which color it is showing. So depends on that, it will be the distance will be calculated. Okay, so that is another type of thermal imaging. Some cameras also we will just flash type, that is also due to black body only. Okay, illustrating its broad relevance in science and technology. These are the spectral representation as well as the application of black body. Okay, so now there is a second one. Second classical mechanics is not explained, that is a photoelectric effect. Okay, so the photoelectric effect we know earlier also, that is when electromagnetic radiation shines on a clean metal surface, electrons are emitted from the surface. So this phenomenon we call it as a photoelectric effect. When the photons are emitted, that electrons are emitted from that material, they call it as a photons. Okay, so whenever this current is coming through this phenomenon, we call it as a photocurrent. Okay, this is a photoelectric effect. This one. Okay, but this was discovered around 1987 by the German physicist, that is Heinrich Rudolf Hertz. So this in terms of Hertz, we have units for frequency. So that scientist name is this one only, Hertz. Okay, so here the photoelectric effect is discovered by German physicist around 1887. But this photoelectric effect, so the Nobel Prize is got Einstein. Okay, that's a different story. So where this material, that is anode and cathodes. Okay, if the incident the ray is incident on the metal surface, the electrons will be ejected. You can see there is a blue dots will be there here. It will be ejected from this material. So it will be connected through another electrode. Then there will be current flow will come here. Okay, so that is the photoelectric effect. Okay, so this photoelectric effect is a lot of applications are there, because our solar energy, that is most of these energies, like for solar cells, these there is a astronomical use also, they use these solar cells, because there is no connection between electricity is we cannot means transfer from earth to satellite. So there is a coated with this solar cells, that is a photoelectric effect is using solar cells. That solar cells are they used to generate the current for satellite purpose. Okay, this actual phenomena is like this. If the ray is incident on the metal surface, then there is a cells will be there. Na? You all know that there is a 1s2, 2s2, 2p6. Okay, so if that energy is sufficient, so then that one electron, if you want to remove from here to other place, then you require some sufficient energy. If whatever the energy it is not correct, so it will be some sufficient energy required of that photon, then only the electron will be ejected. So this ejected electron will be collected through this some circuit, then you will, it means the electron flow is nothing but current. So that current will be generated through this photoelectric effect. So when you are giving some energy, okay, so that frequency, whatever we call it as the frequency, different wavelengths will be there. So up to this point, the current will be zero. In that means if you are incidenting this type of wavelengths, so you won't get any electrons ejected. So that means there will be no current flow will in that circuit. So at particular point, that is call it as a threshold frequency. We call it as a threshold frequency. This threshold frequency is every material, it depends. If one material threshold frequency is some value, then other material may not be same. So it will change. Okay. So this is a material property, that is a threshold frequency. After this, the electron flow will come. That means the ejecting electrons will come. So this particular frequency is required. So this required frequency, we call it as a threshold frequency. So then if electrons will be ejected, then if you are go on increasing the frequency of that light, so then it will be saturating at that point. So this saturation current will come. So this saturation current, is it depends on the intensity or not? It will be depends on intensity. If the lower intensity, you will get the small electrons, means less electrons will be ejected. Whereas if your material is incident by high intense light, then you will get the more electrons will be ejected. So this spectral representation, once again, it will be connected with the threshold frequency and intensity. So you have to write this photoelectric effect definition and how it will be constructed. This is the frequency dependent electron ejecting. Okay, number of electrons, how it will be ejecting, we will explain according to this. So there is actually video, so now it's okay. So these two properties where the quantum mechanics is prevail in that two properties, like a black body and photoelectric effect. So in these two effects, there is a electrons are ejecting. So that means the electrons will be more dominating. That means the particles are dominating. In earlier days, it will be like a wave. That means light means we will say it will be wave nature, because diffraction, interference, polarization, all are these properties are related to wave nature. So whereas this some of the experiments earlier, this photoelectric effect or Compton effect or black body radiation, these all are related to particle nature. So that means some people will say it's a light is particle, some people will say it's a light is wave. Then finally there is a confusion in between. Then finally this fellow, that is Louis de Broglie, so he made a bold suggestion. This theoretician de Broglie, so, okay, so is Louis de Broglie, is the student of his father. Okay, so when he was in a PhD student, he make this type of suggestion. So he said, if the radiation, which is basically a wave, exhibit particle nature under certain circumstances, that means some experiments, it will call it as a wave nature. But in some other experiments, it will act as a particle nature. That means if the electromagnetic radiation, it behaves like a wave as well as particle. So that he said that phenomenon, that suggestion, he called it as a dual nature of the particle. If the particle is moving with high velocity, it will go to wave nature also. If the electromagnetic wave is like a particle, so that means it's both will be there, particle nature as well as wave nature, but it is depends on the experiment. It depends on the circumstance, which one you are using, that will be depends. Okay, so it can act like a wave sometimes and like a particle at some other time. Then these all matters usually thought of as a particle, which is wave like behavior. That means light is a wave, and similarly particle is a wave also. That means light act as a wave as well as particle, then particle act as a wave as well as particle. That means it's a dual nature of the electromagnetic radiation. Okay, so this is the de Broglie hypothesis. That is he made some suggestion, because earlier that there is a lot of differences will be there. So for this purpose, he made some mathematical expression. Okay, so the energy exhibits wave particle duality, that is sometimes behave as a wave and some other time it will behave as a particle. So these type of waves we call it as a matter waves. So actually according to Planck's theory, so the radiation of energy, that means E is equal to h nu. E is equal to h nu. Nu is, once again it will be called it as a, nu is a c by lambda, light velocity divided by wavelength, that is a frequency. Okay, so this this energy, that is according to Planck's theory, the radiation. So we are talking about the radiation. So this energy is equal to h into nu, or h into c by lambda, h into c by lambda. So this is the energy. So then once again it's c is the light velocity, lambda is the wavelength. So then there is a electromagnetic radiation. One more relation is there, that is according to Einstein mass energy relation, that we call it as a E is equal to mc square. Okay, E is equal to mc square. So this also electromagnetic radiation, this is also energy for mass energy relation. So these two, we will equalize these two equations, it becomes hc by lambda is equal to mc square. Okay, so then c will be cancelled out, then lambda is equal to h by mc. So this means is suggestion according to de Broglie. This suggested by de Broglie. That's why we call it as a, this wavelength we call it as a de Broglie wavelength. Okay, de Broglie wavelength is equal to h by mc. So this is a light velocity. If the particle, we are considering like the particle is moving with velocity with mass m and velocity v, then the wavelength of this lambda value, that is lambda is equal to h by mv. Instead of c, it will be the particle velocity. Mass of the particle will be same. So lambda h is the Planck's constant, that is 6.62 into 10 to the power of minus 34. So whereas the mass of the electron as well as the velocity of the electron, if you consider the electron, otherwise it's the mass of the some body, velocity of that body. So that depends on that one. Okay, so this one equation, h lambda is equal to h by mv. So m into v we call it as a momentum. So then that equation becomes h by p. That is also de Broglie wavelength equation. Okay, so this is equation 1. So then if it is a particle is moving with velocity, means what? There will be some kinetic energy will be there. So that kinetic energy is equal to E is equal to half mv square. Okay, so this kinetic energy, because the particle is moving with velocity v. So then mass of the mass. So if you divide and multiplied by this equation into m, what will, there will be no han. So that means it becomes half m square v square by m. Okay, so because we want to replace this m square v square with this equation, so m square v square is equal to how much? It will be m square v square is equal to half, sorry, not half, 2em. Okay, so that means p square is equal to 2em. So then p is equal to root of em, 2em. Okay, so this p we will substitute in de Broglie equation, where lambda is equal to h by p. Okay, so p is equal to h by root of 2m into e. So this is the another equation related to energy, de Broglie wavelength. Okay, so there is a second equation, lambda is equal to h by root of 2 me. So this is the second equation in de Broglie hypothesis, this one. Okay, so now we studied about particle. Okay, so then if it is a electron, we consider as a electron is moving with the velocity v. So if you particle is, that electron is moving, means you have to apply some potential energy, then only it will move one place to another place, otherwise it will be surrounded by nucleus. So if you want to escape from nucleus, you need give some potential energy. So that potential energy we call it as a capital V. So then only it gain a velocity v, and charge will be almost, we all know that it's electron charge, it's E, mass of the electron will be m. So then the electron is moving. Once again, the kinetic energy will come into picture, that is half mv square. Then energy of electron, how you can calculate the energy of electron? So that means how much potential you are giving, that is depends on that energy. That means E is equal to, that is energy is equal to charge into potential difference. If the potential difference is more, then you will get the more energy. Okay, so that is E into E is equal to small e, that is charge into potential difference. This V and this small v is different. Please remember that. Okay, so then we will equalize these two equations once again. So E is equal to half mv square is equal to E into capital V, that is a potential difference. From this equation, we can calculate the small v, that is the velocity of the electron. It will be root of 2 ev. That means E is equal to root of 2 ev by m. Okay, so this is the equation for velocity. So then with this velocity, we will substitute in wavelength, de Broglie wavelength, h by mv. So that means h by m into root of 2 ev by m. Okay, then lambda is equal to h by root 2 mev. So this is the equation. Earlier one, it will be h by root 2 me. Now it will be h by root 2 mev. So we know all the parameters are constants. One, h is equal to 6.62 into 10 to the power of minus 34 joules for kg something. Okay, then there is a mass of the electron. It is 9.1 into 10 to the power of minus 31 kilo kgs. Then there is a charge of the electron. It will be 1.6 into 10 to the power of minus 19 coulombs. Substitute these values, it becomes 12.26 into 12.26 divided by root V in terms of angstroms. Okay, so this is the de Broglie wavelength according to electron. So this one, if it is considered in terms of nanometer, instead of this one is a 12.26 is angstrom. If you consider one in terms of nanometers, it will be 1.226 divided by root of capital V. This is the potential difference. So if you know the potential difference, so you can calculate how much wavelength it will gain. Okay, so if you know the wavelength, so if you require this much wavelength, then that much the potential difference you have to apply for that electron. Okay, so this is we can calculate directly how much wavelength or how much potential required, depends on which parameter you want to calculate. So this is the de Broglie hypothesis for 3 equations we have to derive. So next, this one is a de Broglie hypothesis, that is only theoretical one. So for theoretical ones, we require some experimental proof, otherwise that theory may not be solved, that may not be good. Okay, so every theory there is a experimental proof required. So for that purpose, there is a 2 scientists, so C.J. Davison and Germer in from USA. They made some experiment. This is around 1927, after 3 years, because de Broglie is around 1924. So this after 3 years, they made Davison and Germer some experimental. So then they found it will be demonstrating wave-like property as well as particle-like. So that means his experiment is proof of de Broglie hypothesis. Okay, so Davison Germer is the first time proved the wave nature of the electron verified by de Broglie equation. Okay, so that is around 1927, but de Broglie hypothesis came into 1924. So this is once again it will be experimental proof of quantum physics also. Okay, so how it will be, the Davison Germer experiment, how it looks. So the experiment will be like this. So there is a 3 different parts will be there in this experiment. In his experiment, there is a electron gun and target and detector. Okay, so it looks to be like this. The electron gun means, once again, it is contains filament, that is tungsten filament. If you heat with a small voltage, then the filament will be heat up. Then according to thermionic emission, so the electrons will be ejected. So these electrons will be moving in that direction. Then they will apply the high potential difference here. So then the electrons will gain more kinetic energy and the speed of the electron will be more. So that means the beam of the electron. So that means the electrons are ejecting. We are applying the high potential. Then the beam of electrons will come out. This beam they will reduce using calorimeters. There will be small slits will be there. It will be controlled the thickness of the beam. So the fine thickness of the beam, it will be incident on the target. The target will be nickel target. Similarly, once it is incident on here, so there is a crystal means it will be shining material. Then it will be reflected back. The means that light, that electron beam will be reflected back. So that reflected they will collect through movable detector. So this movable detector, it contains sophisticated galvanometer. So then it will be collect these electrons. Then it will give finally it will give as a intensity. So this experiment looks to be like this. So there is a nickel target and movable detector and electron gun. These are the three parts in this experiment is important. Okay. So how it will behave and how the experiment will be contains, we will study here. So filament, that is electron gun contains filament and electrostatic particle accelerator. It will give you the constant potential. Then calorimeter, what we saw in earlier, that is electron beam will be very thin electron beam will come. So it will be incident on the target. So this electron gun related. Then another one, there is a target. The target is nickel crystal. The electron beam is fired normally on the nickel crystal. The crystal is placed so that it can be rotated about its axis. That means that crystal we can rotate according to the incident angle. We require some particular angle. Okay. So here this crystal we can rotate. So that is the target one. So then third one is a detector, is detecting, capture the scattered electrons from the nickel crystal. This will be moved semicircular arc. There is a some arc will be there. You can see here. It will be movable. So where the maximum intensity is coming, they will calculate. So according to that, so there is a calculation part will be there. So this detector. So electron gun, target and detector. These three parts will be there in Davison-Germer experiment. Okay. So then it's a, what is the principle behind this? So it will be concept of wave nature of matter. That means the electron, that is the light is moving on that nickel surface. Okay. Then electron beam can be used for diffraction studies in crystals. So that means diffraction study means it's a wave nature. This accelerated electron means particle. So particle becomes wave. Okay. So that is experimental proof of this Davison-Germer experiment. So earlier I told the electron gun, which consists of tungsten filament heated by low battery, that is B1. So then it will be, then electrons are ejecting. Those electrons, there is a accelerated by high tension source, that is a B2. So once the high tension source is there, then there is a collimated small slits will be there. Then the beam will be very thin beam will come. Then there is a pinhole will be here. There is a small hole here. So this from this hole the electron beam is coming out. Okay. So then it will be incident on the nickel crystal. So the fast moving electron is made to strike the target of nickel crystal. Then there is a scattered electrons will be in all directions, but at a particular direction that detector will be detected in some angles. Okay. So that is according to atomic planes. So this galvanometer is there will be deflection will come. This deflection is depends on the angle. So this incident ray, then there is a scattered ray. So this nickel crystal. Okay. So if the scattered ray and incident ray, so then they observed this angle between these two is theta is equal to 50 degrees, then only they got in galvanometer deflection is high. That means very intense intensity, very high intensity came at 50 degrees. Okay. So this observation, one observation. Then there is a second observation. So if they are using that voltage, so there is a high potential voltage is there, na? This high potential B2. So at particular value, that particular value is 54 degrees. So this 54 volts, 54 volts, then there will be maximum intensity is come in picture. So these two are observations. One is 50 degrees, another one is 54 volts. If you are increasing the voltage, then the intensity becomes less, whereas the lower voltage also the intensity less. Similarly, the angle is above 50 degrees, it will be less intense. Similarly, lower angles also less intensity. So that means these two observations are important for this nickel crystal, that is Davison-Germer experiment, these two observations. So from these two observations, how we will prove it will be dual nature of the particle. Okay. So then there is a potential difference. So we have a means de Broglie wavelength according to electron. So that is 12.26 divided by capital root V. So using this equation, so we will get the wavelength of 1.66 angstrom, because root of 54 here. 12.26 divided by root V, root 54, the value will be 1.66 angstrom. Okay. So in another observation, we have a 50 degrees. This 50 degrees is incident to scattered, but actual crystalline planes will be different. So you know the crystal means it will be array, means proper array of atoms. So this then they call it as a planes, Bragg planes. So in this Bragg planes and this incident scattered one, the angle will be different. So in the Bragg planes, it will be incident the angle of 65 degrees, angle of 65 degrees. That is according to Bragg planes. Whereas the incident and scattered one, it will be 50, but the crystal Bragg planes, it will be 65 degrees. Okay. So this 65 degrees, then there is a Bragg equation is there, that is 2d sin theta is equal to n lambda. These all are known ones, Bragg equation. Using this Bragg equation, we will calculate the lambda value. So here n will be first order one, that is 1, n is equal to 1. Then this d is the displacement distance. That means one plane of crystal to another plane. Okay. So this the first plane, this another plane. So this distance between these two planes is called, that means Bragg planes. It is not a plane, means it's not simple one. It's a crystalline planes. That is a Bragg planes. That's a d value. So this d value is constant for every different samples as a different displacement. That means a d value. Okay. So this in a nickel crystal, it will be 0.92 angstroms. Okay. So that is crystal displacement plane distance. Okay. This they already calculated, so it's this experiment. Okay. That is 0.92. Then sine of 90 minus 50 by 2. So 25 minus 90 minus 25, it becomes 65 degrees. Okay. Sine 65. Then lambda value will be 1.67. So this is a diffraction type. Okay. So that means the ray, incident ray and scattered ray. So this is diffraction type. That means this is a wave nature. The particle is in terms of wave. So here wave nature, it will be 1.67 angstroms, that is the lambda value. Whereas this one 54 volts of is incident on, that means 54 volts, the electron will be gain some energy. So this 54 volts is particle nature. That means it's electron. So this is particle nature. The value will be 1.66 angstroms. So the 1.66 and 1.67 is almost similar. So almost same. Okay. So this close agreement of these values, then they said it will be the theoretical value got the same de Broglie equation. Okay. Then these two equations, because of these two equations, we will verify the de Broglie wavelength or de Broglie dual nature of the particle. Okay. So that means this particle nature wavelength is same. Similarly, wave nature wavelength also same. That's why it is the first proof of de Broglie hypothesis, that is Davison-Germer experiment.